Hey everyone, Mr. Fott here. Today we're going to be going over the last of these questions. That way, again, you can check your work just so you can see where potentially you might need to make some necessary corrections. So this is going to be for 6 through 8 of our practice problems. 1 through 5 are going to be in the first recording. So for question number 6, it reads this. A plant cell has a solute potential of negative 7.5 bars. Keeping in a constant volume, it's immersed into an open beaker solution that has a solute potential of negative 4 bars. What is going to be the cell's pressure potential? Well, in this case, it's actually a lot more simple of an answer. So if you think of this, that one of the things that we asked you to memorize, and again, there's not very many things I do ask you to memorize, but that's one of those things, that the pressure potential of, depending on if it's a plant cell or an open beaker, plant cells are going to have a pressure potential value of 1. This is, again, for plant cells. However, if it's going to be a beaker, it would be 0 for beakers, for open beakers. So in this case, there actually is no calculation that you need to do because we had told us right from the beginning, it's a plant cell. What is the pressure potential? It's 1. It's another one of those memorized values. So we don't actually need to do any of our calculations this time around. So that was actually pretty straightforward. 7 and 8, however, are going to be a little more involved. And I'm going to set it up like this. We're going to talk about 2 different situations. We're going to talk about our values for the cell, and then we're going to talk about our values for the solution. So whenever talking about our osmosis, water potential calculations, it's always good to separate it into 2 different categories. So from here, we can identify our different situations. So the solute potential, the pressure potential, and then adding the 2 values, the total water potential. Same thing for the solution. The solute potential, the pressure potential, add the values together to get your total water. So I like to set it up like this, and then I can go, as I'm reading the question, I can go ahead and start to plug in any values that they happen to give me. So in question number 7, it reads, at 20 degrees Celsius, I'm already adding the number in my head, I know that we need Kelvin, so I have to, again, add that 273 value. So I'm going to get to 293 is going to be my temperature with units of Kelvin. It's contained at a 0.6. This is the cell, has a 0.6 molar. That's a concentration. You should already start to be thinking of like where I might want to go with this. If we have a temperature, we have a concentration, right? And we're going to have to use our negative I crit calculation. It's an equilibrium. This is key here. We're going to come back to that in a little bit. It's going to help us answer this question with its surrounding solution. Now, this is the concentration of the cell. Be very careful. This is the concentration of the solution. These 2 go together here. This is actually a little in my way. All right, there we go. So if we keep reading, it says it's glucose, and that's going to be one of our keys. This happens to be a sugar. Again, it has that ose ending. So the I value is going to be 1. Because again, all of our sugars are not going to dissociate into separate things. Those are only reserved for ionic bonds. Our sugars, anything ending in an ose, is going to be a covalent bond, meaning it's going to have an I value of 1. In an open container, that's also key here. What is going to be the cell's pressure potential? So there's a lot of information they gave us, and we are going to have to do that negative I crit calculation in there somewhere. But first off, let's use the information they gave us. So we know that this beaker is an open container. Right off the bat, it has to be a 0. So that pressure potential is 0, which means that the water potential of the solution is the solute potential. These 2 values will be equal to one another once we do the calculation. So we can go ahead and actually run that calculation now for our solute potential of the solution. We have our concentration. We know that they're both going to be sugars. It's 0.6 glucose and then 0.5 glucose. They're both sugars, so they're going to have that I value of 1. So if we use our negative I crit, we get negative 1 times concentration. We're going to do the solution first. So that's 0.5 times our value, another one of those informations that is going to be constant and then times our temperature. Now it says it's equilibrium, which means that the temperature is going to remain consistent between the two containers. So once we do this whole calculation, let me plug this into my calculator, we get -1 times 0.5 times 0.08314 times 293. We get to a value of, this is -12.18. I'm going to leave a few decimals in there. So we know, again, -12.18, -12.18. So we have this. Now this is where this is going to be key. It says the two are in equilibrium, which means water does not have a big push in or out. So they're not going to, this water flow is going to have a no net movement. So these two potentials, the water potentials, are actually equal to one another, and that's key. Whenever they use that word equilibrium, these two, the cell and the solution, will be equal to one another. So that's very key to this whole process, as you can kind of see. We can now use our negative I crit one more time. That way we can run the calculation for the cell. And we really only need to change one value. So instead of our 0.5, we're going to change this to 0.6. So it's going to change just ever so slightly. R will not change, the temperature didn't change, and the I value, it's still glucose, so it's going to have the I value of 1. So I'm going to rerun that calculation like this, just so I can get my new value. So -1 times 0.6 times 0.8314 and 293. Now you can probably make a guess here that the number should be a little bit larger, and in fact it is, because we have a larger value. So we get to -14. Sorry, the absolute value will be larger. The number itself is more negative, so -14.61. So we ran the negative I crit, we got to this, which leaves us, here's still our question. This is ultimately what we're trying to find, but we can do this now. If we use the equation, our water potential is equal to solute plus pressure potential. So we simply need to subtract, our solute potential from both sides. So if we look at it like this, water potential minus solute potential is equal to the pressure potential. We're using some of our algebra knowledge here to then finish up this problem. So now we can plug and chug. So we know that our water potential was -12.18 minus solute potential, -14.61. Notice how I'm using the parentheses so I don't confuse myself. So we're trying to subtract a negative number, so really it's like addition, but I like to use the parentheses just so I don't get confused. Minus -14.61 should come to a value of 2.43. Done. So we know that this answer actually comes out to, as our final answer, 2.43. Don't forget your units, bars. So these pressure units are going to be, generally speaking, in our units of bars, unless otherwise indicated. So that's where we get our final answer. There we go. Again, the key here was separate it into 1/2 cell and then 1/2 solution, and then equilibrium. This is going to be key, that the two water potentials will be equal for the cell and the solution because it mentions equilibrium. Okay, let's do the last one. We're going to set it up doing a similar thing. A little more room for myself. So we're going to do a very similar thing to what we did last time. So we're going to set up our cell, our solution. Two different scenarios here. We have our solute potential, pressure potential, add the two values to get our water potential. Same thing over here. Solute, pressure, add the values to get to the water potential. Add some equal signs. All right, now we're ready to read the question. Number 8 reads, at 20 degrees Celsius. So once again, we have to add that 273 So we have it in units of Kelvin. So we have a temperature, which means we're probably going to need to run that negative I crit calculation one more time. It says a cell with a pressure potential of 3. Fantastic. I'm going to start to fill that in. It's telling us it's 3 bars. Is in equilibrium. That's key, which means these two values will be equal to one another. So once we find one, we found the other. It has a surrounding 0.4 molar solution. So now this is in the into the beaker. So we know that the solution concentration on the outside is this. So now we have a temperature, we have a concentration. We know it's sucrose. There's another sugar. It's got that ose. So that I value, we already know what it's going to be. It's going to be 1. So here again, we can start to see where we're going to do this negative I crit. It also states that it's in an open beaker, which means the solution has a pressure potential of 0, so a solute potential is the water potential. And we're ultimately going to find out what is the molar concentration of the sucrose of the cell. But before we can get to this, we have to figure out the solute potential before we can get to the actual concentration. So let's start with the solute potential of the solution. So we have to run that negative I crit. We know that it has an I of 1, so negative 1. Concentration says it's a 0.4. R, same value. Never going to change. They're going to give you that number. And then times our temperature, which was 293. And this will give us our solute potential. So negative 1 times 0.4 times 0.314 times 293. We get to a solute potential of negative 9.74. Getting a little ahead of myself. And again, because the pressure potential is an open beaker, it has that pressure potential of 0. We know that this is going to be this value right there. And because it's equilibrium, we also know that value. So it's pretty handy once we know this whole concept of equilibrium, that a lot of things start to fall into place from here. Now, we can figure out, again, using our equation, water potential is equal to solute plus pressure potential. We need to figure out the solute. So minus or subtract from both sides. Again, using fancy algebra knowledge, we can do that. So we need to know water potential minus pressure potential is equal to solute potential. Plug and jug. We know the water potential was negative 9.74 minus our pressure potential, which was 3, is equal to, plug that in. Again, it might be handy to use the parentheses as well. 0.74 minus 3. We get to a solute potential of negative 12.74. Now, this didn't give us our concentration quite yet, but we can extrapolate a little bit further. So if we know that the solute potential is equal to the negative ICRT, well, there's our C right there. That's what we're trying to figure out. What is the concentration of the sucrose, the sugar that's in the cell? So we can use the solute potential of the cell to figure this out. R, we already know that. Temperature, that's 293. The I value, well, it's sucrose, so it's 1. And this is going to be our mystery or our unknown variable in this situation, so we can calculate that. So what we can do, again, using some fancy algebra knowledge, we can simply divide, since these are all being multiplied, do the opposite. Let's divide by negative IRT, which you do to one side, you have to do to the other, negative IRT. So if we clean this up, our solute potential, and actually start plugging in numbers, so we can start to get to our answer. So I know my solute potential was negative 12.74 divided by negative 1, 0.08314, and then 293. So if I multiply my denominator values to get that into one value, that might help a little bit. Times 3. So if I clean this up, we get to negative 12.74 divided by negative 24.36. There we go. So all I did was carry out this denominator. So now I have basically just made a fraction. And because we have a negative divided by a negative, it's going to result in a positive value. So we're on the right track. Negative 24.36. We get to a concentration of 0.522. This is our capital M for molarity. Fantastic. So this is how we would walk through those calculations. If you need any further assistance, please let me know. You can always email me. We can set up a time. I've got office hours. Whatever you need, please let me know. Thank you all for watching. Have a fantastic day.